Okay, so hi everyone, I'm Kshitij, and today we will be discussing homework 3 problems. I'll be going over the outline of the problems, but not the entire solution. So let's get started. And also, I'll tell you if you need some information or not, if that has been one of your doubts regarding this. So it says consider Navian airplane whose wing layout is shown in figure 1 and has the following characteristics. Assess airplane's roll stability. You may approximate the wing shape as a trapezoidal wing. So how do you go out and approximate roll stability? So to approximate roll stability, you need to understand that you need to have, what do you say? You need to have the capability to measure how does roll get affected with side slip, and obviously how do we mitigate it using the dihedral. That is why the dihedral is provided in the first place. So let's see. Let's recall from first principles just so that you remember. Remember that if you go and visit lecture 6 handout notes, you will see that because of the side slip and the dihedral combined, we can say that the wings together, they see a change in angle of attack, which we quantify as V sine beta. This is small v, so it would be better to use cursive for this. And this is cap v, or the complete velocity. And then we know that v over v, like small, this is sine gamma, sorry. And then we know that small v over cap v is going to be sine beta or side slip times sine gamma. And because beta and gamma are of both small angles, so we can approximate them as beta times gamma. And obviously, this has to be done in radians, not in degrees. So now you go ahead and you say that, okay, this is um, this is fine. But then you ask that because of this change of angle in attack, because of this change in angle of attack, what is going to happen is there will be a change in lift force. So you go some distance y into the wing and you choose a small element that is of length dy. So we are getting into calculus. And then we try to find out that what is the change in lift at this location y. So it will be straightforward. The dynamic head at that point, the chord at that point, which is a function of y, times dy. So this is your S or platform area for this small strip of the wing. And then you go ahead and multiply CL alpha times beta gamma. But you will think that, okay, CL alpha also, I should be careful. This is, since we are dealing with an actual aircraft, this has to be capital L or 3D alpha. So remember that there is a trick which will probably require me to share with you, is that if CL alpha is not provided, then usually you can assume that this 2D CL alpha or CL 2D, that is for the 2D case, is going to be 2 pi. And then you can use the aspect ratio to get the 3D CL alpha. Okay, so I provided you with one hint here. Now the question arises that if we have a change in lift, then obviously we are going to have a change in the rolling moment, which is nothing else but simply change in the lift at a section y times y, and then we want to integrate it from 0 to b over 2, and then we want to multiply 2 with it, and obviously this will be in the negative sign. So this will give you an expression in terms of beta, gamma, CL alpha, so on and so forth. And obviously we are looking for CL beta. So now when you take the derivative with respect to beta, beta will go away. And the only thing that will remain is the contribution of the dihedral to CL beta would be negative 2 integral 0 to b by 2 chord as a function of y times y dy whole divided by platform area times C cap L alpha for the wing times the dihedral. The rest is straightforward. There is an important statement mentioned here. Um, so you may approximate the wing shape as a trapezoidal wing, which means that if you go and refer lecture 6 handout notes or even chapter 1 or lecture 1 handout notes, you are going to find out that you can calculate. I mean, it's not something very difficult to derive yourself, but I am providing you in case you do not find it. So chord as a function of y is given as the root chord or C sub r times 1 plus lambda minus 1 times y over b by 2, where lambda is nothing but the taper ratio. And how is taper ratio defined? Taper ratio is defined as C tip by C root. So I will expand this so that you remember this is C tip by C root. So if you look at the information in the question, what is provided to you? B by 2 is provided to you, which means you have the wingspan, you have the root chord, you have the tip chord, and you have gamma. So there's nothing which you do not have in this expression. This is not a very difficult question. However, the objective of this question is to help you recall this core concept while assessing the roll stability of the aircraft. Are there any questions? Okay. Moving forward, what is the next question?
Hey, Shittish. This
Yeah.
isn't like a question, but like, do you mind posting the Zoom link to this office hours on campus again? I think people were asking in the Discord what the link was.
Oh, I have already posted it on the announcements. Do people not have it on the announcements?
I don't know. People seem confused.
Okay, I'll just post it online.
Yeah. Thanks.
I have put an announcement. You can let them know the link is there.
Okay. Thanks.
Yeah. And let me check. Did I actually forget to? Oh, yeah, I forgot to put the meeting link. That's my fault. No issues. Let people come on in and I'll take up any more questions if they have. Okay, so moving on. A twin engine airplane has the following characteristics. We have the platform area is 900 feet square, blah, blah, blah. Not important right now, but a lot of information about the vertical tail and rudder area. So first of all, we have been asked to estimate Cn delta R and Cl delta R. So nothing very daunting here, to be honest. So whenever you are asked to estimate, first of all, your first job is to go ahead and write down the expression for Cn delta R, which is nothing but minus eta V vo volume ratio for the vertical stabilizer, Cl alpha for the vertical tail, sorry, not stabilizer, and then tau R. So it turns out that if you look at the question, eta V is provided, so we are good. And we are not given this directly, but if you recall the expression for it, it is the platform area of the vertical tail times the length to the vertical tail divided by wing and wing and span. Wings, platform area and span. All of this is provided. Wing platform, wing span, area of the vertical tail, and as well as the length to the vertical tail, aerodynamic center of the vertical tail. So we are good with one more variable. CL alpha is again not provided. So I'll reiterate what I said earlier. So you can assume that CL alpha for 2D is approximately 2 pi. Then use this information with the aspect ratio of the vertical tail to finally get the 3D CL alpha for the vertical tail. Plug that in here. You get this value as well. And then you have tau rudder. So tau rudder again is going to be a function of area of the rudder divided by, actually, I should write something like this. It's going to be a function of area of the rudder divided by area of the vertical tail. So you go ahead, look at lecture 4 notes. There is a graph like this which shows tau versus S rudder over S vertical tail. Once you have, so you have S vertical tail, you have S vertical tail, you have S rudder, so you have the ratio. You just need to go and look up tau's value. So C and delta are nothing difficult, straightforward, finding a lot of information and putting it together. Next is CL delta R. We'll do the same thing for CL delta R. So if you go ahead and write down CL delta R, remember that it can simply be determined as negative ZV LV times C and delta R. So we already have C and delta R and ZV is given to us. So LV is also provided to us. So these are just routine exercises for you to learn where to look. So you should always be keeping the lecture notes handy, the typed out lecture notes with short formulae and expressions. And I would very strongly encourage you to make a two-sided sheet of your own starting now. What things are important, what things come up again and again, because in the midterm and the end term, you'll be allowed, like, in the end term, maybe two sheets, but in the midterm, one sheet of formulae back and forth. Obviously, you can't fit all of the lecture notes on there. So you need to study and identify that what's important and put it on there. Okay, so first part is done. Then estimate the signed rudder deflection required to trim the airplane if the left engine fails at a flight condition of 196 feet per second at some density. No issues. So let's go and tackle this. So once we have that, what do we need is we need the moment due to this thrust asymmetry, right? So the left engine has failed. If the left engine has failed, okay, you are not given thrust information, or you are given, yeah. So each engine delivers 9,000 pounds of thrust and 11 feet is the lateral offset. So which means that always go ahead and make a diagram first. Nothing fancy, just a stick figure will do, right? There is one engine here and there is one engine here, and we have been told that each of them is throwing out 9,000 pounds of thrust. And which engine has failed? That's important because you have been asked to specifically give it the signed rudder deflection. So if you get the sign wrong, I mean, it's not just a matter of question, but it's a matter of just understanding the problem as well. So the left engine has failed. Okay. So what was happening earlier? We were getting 9,000 pounds of thrust here and 9,000 pounds of thrust here, and both of these were 11 feet away. Now all of a sudden, this 9,000 pounds of thrust is gone, which means that now about the center of gravity, you have a yawing moment. You have a yawing moment coming out of the thrust. And as you can see, that this is like Z positive is Z downwards is negative. So this is going to be a negative yawing moment, right? Which means that whatever my thrust, whatever my rudder is going to create, the yawing moment that I require from my rudder should balance out the yawing moment from the engine or due to the thrust. And rest is pretty straightforward because NR is what? NR is again some, if you non-dimensionalize it, what do you non-dimensionalize it with? You non-dimensionalize it with Q, S, B, then C and delta R is the coefficient times delta R. So now you have all of this, you can find this. Remember the sign is negative because we are pointing downward, Z is positive. So when you point your thumb in the direction of Z, this direction is positive yawing moment, but the thrust is going to create this moment. So take care of the sign. And even after you get the answer, make sense. Go back to lecture 7. Even when I was an undergrad kid, like I would go back to the table and make sure that my signs are right, because even today I am not at all ashamed to accept that I get the signs wrong, because it's difficult. It's non-conventional, it's non-intuitive. So you need to practice a lot and be careful. Lastly, I think here I would like to address one of the doubts that came up from one of the people. So let's read out this question. If the aileron effectiveness is CL delta A, which is given, what would be the signed associated aileron deflection required to trim the plane? So first of all, a lot of you are getting perplexed that why would we need an aileron deflection? Because I told you in discussion sessions as well as in the lectures also, it's sometimes it's okay, it's sometimes you miss out the bigger picture when the subject is new. But get this, why did we study pitching moment or um, longitudinal stability first and then directional and lateral stability together? Because directional and lateral dynamics are coupled. When you are yawing, you will induce some roll moment. When you are trying to roll, you will induce some yawing moment. So because we are giving a deflection on our rudder, we are going to induce a rolling moment. Okay. And that is why we calculated CL delta R. So once we have CL delta R, we know now rudder engine combination is set. We are trimmed in yaw, but deflecting the rudder did create a disbalance in roll. So now we need to trim in roll. So it's simple, nothing else. That is the roll contribution coming from the rudder plus the roll contribution coming from the aileron must sum up to 0. We know the expression for this. Multiply QSP times CL delta R times whatever deflection you had given. And this is coming from balancing NT. Remember that here we were balancing the yawing thrust, the yawing moment coming from the thrust with the yawing moment by rudder deflection. So you'll plug in this rudder deflection to get how much rolling moment you are creating because of the rudder deflection. And then you are going to simply plug in the expanded form for this moment and go ahead and find out the deflected aileron numbers. And remember that write down is positive. Yes, I guess write down is positive. Still confirm I may be wrong, but go back to lecture 7. Look at the sign conventions and make sure that your sign is correct. So since I've been repeating this multiple times, by now I think you know that the positive negative directions of rolling moment, pitching moment, yawing moment, and the positive negative directions of elevator deflection, rudder deflection, and aileron deflection should definitely be there on your midterm cheat sheet. At least in my opinion. I was never good with it. Still am not. Lastly, consider the problem introduced in the last discussion session, that is following an airplane. So it's the last problem is very similar to the discussion. So if you recall, I have sent out discussion notes and discussion recall PDF. I have solved the problem there as a sample solution, and this is just asking you to execute it on 3 other aircrafts. But just to give you a short recap, it's that if you have a large aircraft, and if I'm looking at it from behind, and this is going in the forward direction or leaving the runway, then it is going to leave trailing vortices like this. And if you try to fly a smaller aircraft into the trailing vortex behind, so if I have a smaller aircraft here, then this smaller aircraft will face the trailing vortex, which will cause a rolling moment. And the only way you have to negate for that rolling moment are ailerons. So you need to check that in the wake of a Boeing 747, which of these aircrafts is going to survive if they unfortunately get caught in its wake. So this is not very different from, this is not absolutely different from the example problem we discussed. It's just for your practice. So I think that winds up all the questions on the homework. Is there anything that someone would like to specifically ask about so that it gets into the recording and other people can benefit from those?
I think I joined the discussion a little late because I received the link a little bit late, but I was
Yeah,
wondering.
that's my fault. Yeah, yeah,
Yeah, no worries. Um, I think for number one,
yeah.
I
Mm-hmm.
think the roll stability depends on the coefficient should be, I think, less than zero. But I was wondering
Yes.
exactly what that coefficient was or how
Oh,
to calculate it.
so yeah, so recall from so I'll just draw in something. I'll just copy a picture. So if you go and look at lecture, this is which lecture? This is lecture 6 handout notes, figure 3. Okay. So what happens when I look at the aircraft, right? I'm looking at it from the back. So this is the tail of the aircraft here, something like this. So if you have a side slip, that means you have a V which is non-zero, then what happens is one of these is going to see an increase in lift, the right hand side wing, and the other one is going to see a decrease in lift because they'll see a negative angle of attack, right? So first of all, we need to go at the root. Root is both the wings are seeing a change in angle of attack because of the side slip and the dihedral combined. And what is this given as? Small v times sine gamma over cap v, where small v is actually the component of the velocity which is causing the side slip, and cap v is the total velocity, which is root over u square plus v square plus dub square. And small v over cap v is sine beta, sine gamma. If you multiply, if you apply the small angle approximation, which has been like multiple times discussed multiple times, then it simply becomes beta times gamma. So now if there is a change in angle of attack, there will be a change in lift, right? But this wing has a varying platform. So we have to do some differential calculus. We say that, hold on. Yeah. We say that we'll start here at the root and we go some distance y and we choose a tiny strip of width dy. So what's the width? What's the area of this strip? The area of this strip is going to be simply the chord length at this location, which is obviously going to be a function of y times dy. So you go ahead and write down the change in lift is dynamic head times the platform area times lift coefficient times beta gamma. The lift coefficient is not provided in this example. Whenever in this problem, whenever it's not provided, you can assume that it's 2 pi for the 2D case. You have the aspect ratio, you can calculate the aspect ratio, and then you can use these two pieces of information to get the 3D lift coefficient, which you will finally plug in here. Once you have that, then you'll go ahead and calculate the rolling moment, and then you will non-dimensionalize it to get the contribution to CL beta from the dihedral, which will be given by this big expression. And we have gamma, you will find out CL alpha wing, you have the aspect ratio, you have the platform of the wing, you have the span of the wing. The only thing you need to evaluate is this integral. And the function here, chord as a function of y, this expression is there in lecture 6 as well as lecture 1 notes. So if you have a trapezoidal wing, which the question says you can assume, the chord function, the chord as a function of y is given as chord at the root, times 1 plus gamma minus 1 divided by y over b by 2. And this gamma is nothing but taper ratio, which is c tip by c root. So once you plug in this function here into the integral, do the integration. Now you have this, 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 you have contribution of the dihedral to Cl beta. So assess, as in you need to get a number, show that it's negative, and say that yes, we expect the roll stability coefficient to be negative with respect to beta. Does that answer your question?
Yes, thank you so much.
Anyone else? Okay, so I'm going to stop the recording here, but I'm going to stick in the meeting for until 6:30.